Thank you very much. I want to especially thank Yuri Lozitsky for arranging this visit here and the departments for all the support. And my wife and I are very, very happy to be able to combine this with a trip to Heidelberg, Vienna here, and then we'll go to Berlin before returning home. And so it's really a great opportunity to meet a lot of people, especially old friends, to be here. So thank you very much. I began to realize that if you live long enough, you become an historical figure. I don't mean a historical figure like Mendel or Einstein or Napoleon or that. It's just that I've been very lucky in my life to be in many different places and meet many interesting people, and many of them had such a strong influence on what I then tried to work on and study. And so I want to share with you today some memories of these people, because what's historical is I've met them and you won't be able to meet them. And so I'm part of the historical context in that sense. So this will be concerned with something which logicians call lambda calculus, but in basic terms it means, can you eliminate types and have a type-free theory of functions where a function can take itself as an argument. If you ask it that way, it sounds completely crazy, because the ordinary functions that you know in mathematics don't take themselves as arguments. But the logicians kept asking if there's something possible there, and maybe it has some importance for logical foundations. And so let me tell you a bit of where it came from. I'm hearing a bit of echo in here. Is the PA system too loud? Is it too loud? Is it okay? Yeah, okay. Now, very lucky, and what I've done, I've given to Rositsky some files that I compiled here, but I would, if you're interested in lambda calculus, then these two authors wrote an extremely good history with lots of references and things like that, and so I strongly recommend looking at that if you want to trace the history. It could perhaps go back to Frege, but I think it starts in the modern time here with Schoenfinkel. He was a rather strange character, apparently. He studied with the Hilbert School in Göttingen, and he wrote an article about Bausteine. These are these operators that can operate on functions and combine them in several ways. For example, composition is an operator that takes two functions and produces a new function. And so there are all these operators that he looked at, and you're lucky there's an English translation of that paper there in the Van Hanenort volume. Now, in the early 30s, Haskell Curry came to Göttingen to do his PhD. In that period, 20s, 30s, it wasn't so common to get a PhD in the States. People often came to Germany to study. And Curry didn't meet Schoenfinkel, but he discovered that paper that had been published. Curry's interest was in foundations of formalization, and one of the annoying things about formalizing languages is involved with substitution of one expression inside another, which becomes particularly sticky when there are free and bound variables to be involved. And so Curry wanted to analyze a process of substitution, and so he thought of various kinds of operators, and then he realized that Schoenfinkel had already had an insight there, and he went on from there. Now, the way I got into this was when I was a second-year student in Berkeley in 51, 52. I found Rosenblum's little book on elements of mathematical logic, which covered all kinds of things about axiomatization, set theory, and other things. And there was a section on lambda calculus and combinators. And I remember vividly that I spent all day trying to understand what combinators were. And when I went to bed that night, I had horrible nightmares that these giant combinators were coming to eat me or something. And maybe that nightmare has affected my whole career. I'll let the psychiatrist figure that one out. But that's when I started to hear about Curry's work. And then, of course, it was closely related to Church's work. But what I want to say about Curry is he's the second most syntactical person I ever met. The most syntactical person I ever met was Ad van Wijngaarden from the Netherlands. Van Wijngaarden came from applied mathematics and then was very influential in the beginnings of building computers and computer programming. And he really felt all of mathematics is symbol manipulation. And of course, it's a little hard to argue against that philosophy, because how do you express mathematics except by symbol manipulation? But on the other hand, some people feel that there's something more in semantics and understanding of mathematical concepts. And I was so glad I was never on any of the Algol committees, because they fought violently over the formulation of those Algol's family of programming languages. And for Algol, 68 van Wijngaarden was finally won out. And actually, it might be interesting to go back and look at Algol 68 because of his two-level type of grammars for doing complicated recursions do have something interesting to it, and you might be able to use that. When the Algol 68 report came out, I couldn't believe it, because it was typed on an IBM Selectric typewriter, and it must have used at least a dozen different golf balls for different types: mathematical symbols, boldface, italics, Greek, all of that. And so I said, when I met Van Wijngaarden, I said, Ad, how did you get a secretary to type that report? He said, oh, I have a secretary who does everything I want. He typed the whole thing himself. There's only a certain kind of personality that will concentrate on things that way. Now, I studied at Princeton, where Church was the leading logician there. And Church had the idea of solving the Russell paradoxes by passing from not a type-free theory of sets, but a type-free theory of functions. And in the very late 20s and early 30s, he developed his logistic system, including the lambda calculus. I'll explain more about lambda calculus currently there. And luckily, Church luckily with the history of logic, is that I think it was, between 31 and 33, I've forgotten the exact dates, Gödel had done his work in Vienna and had found the incompleteness theorem and also the unprovability of consistency. And von Neumann, who was already at the Institute for Advanced Study, was very, very impressed. In fact, von Neumann, when he first heard Gödel, realized that you wouldn't be able to prove consistency of these systems, and he wrote to Gödel, and Gödel said, I already did that. But anyway, von Neumann was instrumental in bringing Gödel to Princeton, and so Gödel gave very detailed lectures on the incompleteness theorem and his approach. Now, Church had two graduate students. I think they're the second and third of his graduate students. Steve Claney and Barclay Rosser. They took very, very, very careful notes of Gödel's lectures, but they understood Gödel's method, particularly the method of arithmetization. And of course, they were very much involved in questions about what is a computable function. In Gödel's proof, he really only uses primitive recursive functions for syntactical manipulation through Gödel numbers. But of course, it was realized that many other kinds of recursion, and Ackermann, one of Hilbert's students, had already discovered a twofold recursion that's not primitive recursive. And so they knew there was something more to computable functions than just primitive recursive functions. So there was a lot of discussion as to how to say what a computable function is. Now, Gödel, with correspondence with Hebron, had developed an idea of very generalized recursion equations, and so there's a notion called Hebron-Gödel recursions. Church, on the other hand, really felt that his logistic system should give a foundation. Unfortunately, just at that time, his two graduate students proved the system as a logistic system inconsistent. And later, Curry found very simple proof of inconsistencies for those kind of things. But the lambda calculus as an equational theory for giving definitions was very coherent, and Church thought that really it should be used as a foundation. In particular, the integers were represented by iterators. In other words, the number 3 is that operator that takes a function f and produces f of x, iterated 3 times. And it turned out that there were extremely simple definitions that Church and Rosser came up with for addition, multiplication, and exponentiation of iterators. But they didn't know how to define predecessor. If you want to do recursive functions that fall back on previously obtained values, you have to have predecessor of an integer as a key thing there. So Church gave Claney the thesis project to develop arithmetic in his system, and then arithmetic just based on the lambda calculus. And as Claney writes, he went to the dentist one day, and in order to distract his mind from what was happening there, he all of a sudden had a good idea how to define predecessor. Gödel never liked lambda calculus at all and didn't think that it represented a foundation for computability. The problem was, at that time, they didn't understand how to represent data structures in terms of these operators. Kleene found out how to do it, and especially for predecessor, you operate in a way on pairs of things. You have to have a way of making expressions with pairs. And now you start with 0, 0, and then you increment 1 and just copy the other one over. And then you have 0, 1. And now you increment 1 and copy over, and you have 1, 2. So by iteration of operation on pairs, you have an offset, and then it's very easy to pick out the predecessor out of there. And so Kleene was then able to then do all the development of arithmetic that's necessary. Now I have to make another comment there, because in England, Turing had been inspired by lectures on logic to invent the Turing machine, and showed the possibility of unsolvable problems by Turing machine computations. And he was then encouraged to come to America to do his PhD under Church. But after Kleene finished his thesis, he wrote another paper, because he understood data types that you can represent in terms of Gödel numbers and other combinations there. He wrote a paper showing that Erbrand-Gödel computation is equivalent to lambda calculus representation. Kleene had shown how to do recursions in lambda calculus, and so therefore you can simulate, using Gödel's methods, deductions with, say, Gödel numbers using lambda calculus, so that you can represent another formal system using the notation of lambda calculus. But of course, since lambda calculus can be presented in a very straightforward way, using Gödel numbers, Gödel-Erbrand recursions can easily simulate lambda calculus. And so therefore, lambda calculus computability and Gödel-Erbrand computability are equivalent. Then Turing comes. Turing, of course, was a genius. It's a tragedy that we lost him to suicide. But when he got there and had Kleine's paper, he said, oh, I can simulate lambda calculus on Turing machines, and of course, lambda calculus can simulate Turing machines, and so therefore. But Turing is second. We give him all the credit today. But remembering Steve Kleene, who was an amazing character, I want you to give him more credit for the foundations of recursion theory. I never had a chance, of course, to meet Turing, but I was close friends with Robin Gandy, who was Turing's only PhD student, and we were together in Oxford for quite a long period there. And so I do have some secondary connection to Turing that way. In my earlier college times, I was at Berkeley and very much influenced with the Tarski school, and luckily Anita Pfefferman, the wife of one of Tarski's students, Saul Pfefferman, wrote a very good biography of Tarski. When they started their project, I said to them, it's impossible to write a biography about the times in the 20s and 30s in Warsaw. But they did so much research. They went to Poland. They talked to many people, even though so many people were gone. it really is an outstanding biography, and Pfefferman does a lot to include in the presentation an appreciation of Tarski's work in logic. One of Tarski's students, who then I knew very well after the war, was Andrzej Mostowski. He was very clever, very amusing person, extremely fond of him. He had two students, Helena Rasiova and Roman Sikorski, who wrote a book called The Mathematics of Metamathematics, as sort of a pun. In other words, they wanted to apply mathematical ideas to foundations of logic. And they did very much. In particular, Mostowski had realized earlier that interpreting logic, we certainly know how to interpret propositional calculus with Boolean algebras, but if you use complete Boolean algebras with arbitrary meets and joins, soups and ints of subsets of the algebra, the laws of soups and ints are exactly the same as the laws of quantifiers. So Mostowski realized that you could give semantics for logic in terms of complete Boolean algebras, and Rasiova and Sikorski work it out in numberless variations there also for some modal logic and some other logical systems there. But it was really Mostowski's original idea. And by the way, there's a very nice volume that former associates and students of Mostowski put together in 2007 that I can recommend for historical background. I asked the Warsaw people over and over again, why did you concentrate only on first-order logic with the complete Boolean algebras? Why didn't you go to higher-order logic? You know, when we think of going from a set to a power set, those are the two-valued functions. In terms of Boolean terms, we could go from Boolean object to a power object by looking at Boolean-valued functions. You have to be a little bit careful how you do that, but Mostowski and certainly his students could have done it. Moreover, they knew everything they had to know about topology, descriptive set theory. Roman Sikorski was expert in functional analysis. He understood measure theory and everything connected there. But they never thought of interpreting higher order logic in Boolean terms. That came out later through insight after Cohen introduced his types of independence, then the idea came out that you could extend things using Boolean values. But the Warsaw people really missed the boat on that. In 1969, I was at an IFIP working group and met Christopher Strachey, and John McCarthy was there and other people too, and there was a lot of arguing about how to formulate and explain programming languages. And I felt that Strachey had the clearest point, from what I could understand, the clearest point of view on things. And so I arranged in the fall of '69 to go to Oxford to work with Strachey. And now Roger Penrose, the famous Oxford mathematician, had suggested to Strachey that for the kind of binding and general definition features that he wanted to do in programming languages, he should look to the lambda calculus. And Strachey and Peter Landon, his associate, over quite a long period. Did a number of things there, but operating formalistically, just in terms of rules, so to speak. And I told Strachey, you know, the lambda calculus doesn't have any mathematical semantics. It's only a formal manipulative system. Kleene had developed, and students and followers there, much better ideas about higher order recursion and connections with descriptive set theory. And so I said to Strachey, you really should look to the Kleene school there to do it. And so I tried to formulate ways of doing it and set up a certain kind of approach. And then all of a sudden I realized on one Saturday in November, oh my God, if you follow what I'm suggesting from the Kleene developments just a little bit further into infinite dimension, so to speak, you'll find a model for the lambda calculus. And so all the terrible things I said about lambda calculus, I had to eat my words there because it turned out that there are mathematical, easy to describe mathematical interpretations. I'm talking a little bit too much here, I can see. Just remember wonderful Corrado Böhm. He took the lambda calculus very much to heart and did many things that the Curry School didn't realize, in particular the analysis of terms that are in normal form. Böhm has a very important theorem that if they have different normal forms, they really are different. And the Curry School had never proved that. He was a wonderful character, also with a big school in Italy that has followed him. David Park had gone to MIT and worked on Lisp in connection with McCarthy there, and then he came back to England and was there to found the computer science school in Warwick University. And in '69, when I thought of the models for the lambda calculus, Park immediately realized he could give a proof that recursion is very easily expressible in terms of the models, and that was an important development that he saw as soon as I had defined the models. John Reynolds had a long career, and he has a big following on questions of proving properties of programs, security of programs, and other things. And in particular, his separation logic is very, very much followed, and we were close colleagues at Carnegie Mellon in the years that I was there. I met Robin Milner first at Xerox PARC in Stanford, and then he returned to England. But this was after I had developed the ideas for the models and the kind of equational reasoning that you can use on these models. And so Milner took that up, and particularly took up the project of doing computer-aided proofs of that. And so that's in giving computer-aided proofs of the LCF system, logic of computable functions. He had to develop a meta-language for formulating the proof tactics in it, and that became eventually a very important independent programming language, which we refer to just as ML, or there's CAML, Cambridge version, French versions, and other things had a big influence. One person that I particularly was fond of was Dick de Bruin in the Netherlands, and of course he wanted to automate proofs in mathematics as well, and he and his students did a lot of work on automath. Of course, it was a little bit early days, and the capacity of computers was not so good, and so the systems were maybe hard to use. But de Bruijn introduced many interesting ideas. He was an outstanding mathematician on many areas, and in particular, the use of dependent type theories was very important for the ideas that he wanted to show how to formalize mathematics. And also this business of substitution of free and bound variables. He introduced an idea of nameless dummies there. It's very much pursued now. Andy Pitts at Cambridge on nominal logic, ways of encoding binding over complicated expressions. And was very glad to have been a close friend of de Bruijn. I would also like to remember Myhill, Shepherdson, and Rogers, and I'll tell you why a little bit later on. Fundamental people in recursion theory, but an interesting theory there is, just like the Polish school missed the boat on Boolean-valued higher order logic, Myhill, Shepherdson, and Rogers missed the boat on enumeration operators, as I'll explain. And let's remember John McCarthy and the enormous influence of Lisp and the development of AI that he and his many associates started there. McCarthy had been a student at Princeton, not under Church, but under the analyst Solomon Lefschetz. But later on, when he was thinking about things like Lisp, he recalled Church's lambda calculus, but as he writes, he understood the axioms, but he didn't understand anything else in Church's monograph there. But it didn't matter. He took over the part that he needed for formulating things in Lisp. I'd also like to remember, because the modeling that I was involved in also involved quite a bit of topological spaces, and in particular, a notion that I introduced called a continuous lattice. And so under Carl Hoffman and many associates, there was a big development about continuous lattices, and the late Klaus Keimel was instrumental in putting together the Cambridge Press book on continuous lattices and domains, which of course influenced things that I did very much there. I'd also like to recall an old friend of my wife and I. In fact, Raymond Smulyan introduced my wife to me, and the result is we will celebrate tomorrow our 60th wedding anniversary. But Smulyan was full of fun, and besides many puzzle books, he made a storybook using combinators, where he pretended that the combinators were birds and the equations defining combinators were bird calls back and forth there. And so he makes up many funny stories of the birds talking to each other. So let's not forget that, but I recommend you look at that again to have some fun with these things. I would also like to point out that already Turing said with Turing machines, he wished he could introduce random elements. Of course, if you think of a Turing machine as something that is constructed physically, you could always put in a random piece of hardware there that produces random zeros and ones, say. But he certainly felt that it would be good to introduce random elements there. Now, Alan Perlis, who was very influential in computer science, he was one of the founders of the Carnegie Mellon Department and longtime chair of computer science in Yale. He hated Turing machines. I rather hate Turing machines too because programming them is so painful to do. But he made a lot of fun of Turing machines. He liked to write epigrams. And one of his favorite epigrams was about me. You may not understand the pun that he has made with, but the Mormons are called the Church of the Latter-day Saints. That means they're saints that came in the modern era after the old-fashioned saints that we see on the wall there. And so Perlis was very pleased with his pun that he considered lattice theory as being far too abstract to be of any use whatsoever, and so only a saint could really deal with it. However, it turns out that his other epigram there, maybe the lattice theory is very complicated, but there's a part of lattice theory that is very simple, and that's what I'm going to try to convince you of. So let's look at more formally at some of the lambda calculus. And it's very simple kind of theory. You really just have two kinds of terms, a binary operation of application. Don't try to read what application means, just say it's a binary operation. But then you also have a variable binding operator the church called lambda, which binds the variable inside an arbitrary expression m. A good friend of ours is John Addison, retired professor in Berkeley. He is he married Church's daughter. He was an undergraduate at Princeton before he went to study with Claney in Wisconsin, but he married Church's daughter. And I asked John once, John, in talking to Church, did you ever ask him why he chose lambda for his operator? And John couldn't remember. He said, I'll write him a postcard and ask him. So he just on a postcard, he said, Dear Professor Church, he always referred to his father-in-law as Professor Church. Dear Professor Church, Russell had the iota operator and Hilbert had the epsilon operator. Why did you choose lambda for your operator? Well, Church didn't write a letter back. He just annotated the postcard and put it in an envelope. And his total annotation of the postcard about why did you choose lambda was eeny, meeny, miny, mo. It's just a nice Greek letter. It has no metaphysical significance. People have tried to claim that typesetters couldn't type circumflex very well, and they move the circumflex to the line, and that's how you get a lambda that's like a circumflex. But I don't believe that. I don't believe that theory. So now the axioms for lambda calculus are alphabetic variant, of course. That just means if you have bound variables, it doesn't matter what variable you choose for it. You just have to be careful not to confuse free and bound variables. And then the second axiom, Curry called, see, the first axiom is alpha for alphabetic variance. The second axiom, Curry called beta for beta conversion. I asked Curry why he chose beta for that, and his reason was it's the second letter of the Greek alphabet. So the beta principle is if you have a lambda abstract which you apply to an argument, then you can figure out what it means by substituting the argument for the variable. Again, being careful about free and bound variables. And then it's very popular in many of the forms of lambda calculus to have another law that says lambda x f of x is just another name for F, but we'll see how that works out. Now, in giving my models for lambda calculus, I used topology and algebraic lattices, and of course Kleene and other people had partial combinatorial algebras, and Kleene had many interesting ideas. A partial algebra is one where the application operation is not always well defined, and that comes out very naturally when you think of partial recursive functions. But Kleene had other interesting ideas about higher type recursion too. So that's some of the background in doing modeling. But what I want to point out to you is that there's a very garden variety object that we can make use of, namely just the power set of the integers. The integers are needed because you need infinitely many distinct, discrete things. And the power set is needed because you need properties of those individuals in N. But the power set is a very nice topological space by using finite information. A finite set gives you a little bit of information about a possible subset. And so if you think of all the subsets that share that finite amount of information, you can think of that as a neighborhood in a topological space. There are two ways of making the power set into a topological space. One of them is to give finite amount of information about a subset and a finite amount of information about the complement of the subset. That's the compact topology on the power set. That gives you a space equivalent to Cantor's discontinuum. But this is a weaker T0 topology where you only work with positive information, not both positive and negative information at the same time. And so it's easy to, if you want to teach undergraduates a little bit of topology, I claim this is a very nice space there because there's a little exercise there. How do you characterize the open subsets of that space? And so there's an exercise there to prove if you use those neighborhoods, then the open sets are those collections that do what I said there. But even better, in general, you know what a continuous function is between topological spaces. And so in the power set space, it's very nice to describe continuous functions, and again, it's a good exercise to use definitions from a book on point set topology and to see how this works out here. A function from the power set to the power set is continuous just in case a finite amount of information about a function value is already determined by a finite amount of information about the argument. Continuous functions don't have to look at the whole infinite power set before they give a finite amount of output. And so it's, I say, a good exercise to show that that logical formulation about finite subsets is equivalent to the usual definitions of continuity between topological spaces. But even better, the power set space, even though it doesn't have a Hausdorff topology, it has a T0 topology, it's a very rich space, and so I want to convince you of that. Already when I was a baby there in 1936, Alexandrov proved that the power set space and other generalizations are universal, in particular, every countably based T0 space can be found as a subspace of the power set of n. What does T0 mean, by the way? It means a point of the topological space is uniquely determined by its neighborhoods. See, there are stronger conditions about comparing points. For example, in a Hausdorff space, two distinct points can be distinguished by disjoint neighborhoods. But this is a weaker principle that says every point is uniquely determined by its neighborhoods. So now if you want to embed an abstract T0 space into the power set space, you just enumerate the neighborhoods, and then you associate with every point x of your abstract space the indices of the neighborhoods that contain it. And that's in a one-to-one correspondence with the points. And so now it's again a really nice elementary exercise for undergraduates to prove that that's a topological embedding. In other words, not only do we have a continuous mapping from the abstract space into the power set space, but the image of that space is homeomorphic, is an exact topological copy of the given abstract space. Even better is that there are lots and lots and lots of continuous functions there. In fact, the power set space has this property that if you have one space, abstract space, that's a subspace of another space, and if you have a continuous function on the subspace to the power set space, you can always extend it continuously to the larger space, no matter how large that space is. Turns out sometimes the values aren't terribly interesting that you get there, but you have a topological extension. It's not unique in general, but it exists. And so, in other words, if you know the continuous functions from the power set to itself, just by restriction, you know all the continuous functions from one subspace to another space. One notion of continuity covers all those topological spaces embeddable in the power set space. And Martin-Löf wrote a beautiful paper explaining a number of theorems about those that I strongly represent. So not only is the power set space a universal space for topology, it's a universal space for continuous functions. And if you knew about algebraic lattices, you could also prove that you can embed algebraic lattices have topology, and the topology fits very nicely with the power set space. By the way, someone should really look at it. Wikipedia is wonderful. All the time when there are arguments at supper, I take out my iPhone and look up Wikipedia and settle an argument there. If you look for algebraic lattices, you'll find out that it's not a very good entry there. So someone really ought to improve the entry connected with algebraic lattices. But here's the other thing, is that we find that these algebraic lattices, which form a very nice category, Cartesian closed category. Power set of n is a trivial example of an algebraic lattice, and the continuous functions from power set to power set of n form an algebraic lattice, but it's also a continuous retract of the power set. So in other words, if you think of a notion of function that involves continuity, then the power set is a topological space contains a picture of the whole continuous function space there. And so therefore, since it's all inside the same universal space, you'll be able to apply a function to itself as an argument without contradiction. But that's the sort of saintly way to describe those, bringing up ideas from topology and lattice theory. What I want to show you is a much more elementary way of doing it quite explicitly here. So this is where the enumeration operators come in. So in order to define enumeration operators, an enumeration operator is an operator that could be represented by a set of integers with a little bit of encoding. So first we do some encoding of pairs of integers as an integer there. There are many different formulas you could use there, but that's the shortest one I know to write down. Every pair of integers corresponds to an integer. Every integer can be decoded as a pair of integers. But if you can code pairs of integers, you can iterate pairs of pairs of pairs of pairs and code sequences of integers in the style of Lisp there, actually there. Also, you can use those encodings to represent finite sets of integers in very simple ways. So that's Gödel numbering of pairs, sequences, sets, using just very minor amounts of arithmetic to do that. And then one thing that's useful to use here is that if you have a set of integers and have these Gödel numbers, then there's an easy way to collect together all the Gödel numbers of the finite subsets of the set. And so passing from x to x star is the listing of all the finite subsets of the given set x. And now an enumeration operator is determined by a subset of the integers in the following way there. F of x equals that set formation. So the reason it's called an enumeration operator is you think of it this way. You think of F as a lookup table that gives you a connection between a Gödel number and an integer here. Now you slowly enumerate all the finite subsets of x, and every time you see the Gödel number of a finite subset of x, you ask, did the lookup table give us permission to pass from n to m? If the table did, and it might or it might not, then you give m as one of the integers of output to form a set here. So this makes an enumeration operators in terms of a given set of integers and as an input a set of integers, and as a result the set of integers that it's being enumerated according to that scheme. And it's a good exercise for undergraduates to show you get exactly the continuous functions this way. Continuous functions and enumeration operators on the power set of n are the same. So here is our lambda calculus model. You use this formula that I just showed there as a binary operation on sets of integers. But this decoding from f by running through x to find some output there can be reversed. And so lambda abstraction is just the reversal there. Make the lookup table that records the elements of the continuous operation applied to a finite set. Run through all the finite sets, take an element of what you got out of it by that continuous operator, make that set of ordered pairs, and so you have encapsulated the continuous function as a set of integers. And in fact, that way, if you have any continuous operator, big F there, lambda x f of x is the largest lookup table that gives you exactly the behavior of f. And that's why with this interpretation of lambda calculus, lambda x f of x is not equal to f. F might be a very small set, but it has a lot of numbers in it. When you take the full lookup table given by lambda x f of x, you may add a whole lot of redundant information that doesn't hurt anything there. So generally, lambda x f of x, according to these definitions, is larger than f. And very nicely there, another good exercise. If you have additional parameters and apply this definition of lambda abstraction in terms of enumeration operators, you always have continuous function in terms of the remaining variables. And so everything, using the notion of continuous function, fits together very nicely here. Now this is where Myhill, Shepardson, and their paper, and then Hartley Rogers in his book, missed the beat, because Myhill and Shepardson, in defining operators on partial recursive functions, said, oh boy, look at all the operators we can define in this way. Now, Friedberg and Rogers, in giving enumeration operators, wanted to explain certain things about recursively enumerable sets. So Friedberg and Rogers defined application, and Myhill and Shepardson defined abstraction, and nobody ever put 2 and 2 together to make a model for the lambda calculus. If I'd only thought of that in 1957 when I knew all of these people, I would be rich and famous now. That's a great regret. I think I have to skip ahead just a little bit as the time is running on here. The power set of the integers is a lattice. When you start doing these operators, there are monotone properties of the application operation, and so there are various things related to the lattice structure of them. Nice formulas you can have there. Other good thing is there, you also, in terms of enumeration operators, even though you have an operator of many arguments, as long as everything is continuous, you have a definition of computable because you do the abstraction on all the variables, and the recursively enumerable sets are the computable ones. Those are exactly the operators that Hartley, Rogers, and Friedberg like to think about, computable enumeration operators. And then the other way around that David Park discovered that there was a very nice proof for is you can use pure lambda calculus to define fixed points in equations involving these operators. And that leads you to all kinds, fixed points lead you to all kinds of recursion. And so that's a basis for it. And in particular, if you sort of thought of successor, predecessor, and test for zero as multi-valued functions there, you know what they mean on singletons, but now we can apply them continuously to arbitrary sets there. You get all recursively enumerable sets by starting with Curry's combinators, the 3 arithmetic combinators, and then you just apply one to another in as many ways as possible. And that's an enumeration of all possible recursively enumerable sets. In other words, this is the lambda calculus version of the universal Turing machine. I think it's much easier to work with recursion equations than it is to work with programs for Turing machines. And I have to skip over this. You can make a very quick definition of inseparable sets using basic principles in connection with the enumeration operators. But there's more. The power set of n is actually homeomorphic as a topological space to its square, because there's an easy pairing function that takes pairs of sets, takes a copy of the first set on the evens and a copy of the second set on the odds. And so every pair can be represented by a single set, and such representation of pairs can be decoded to find the first and second terms there. The power set is the same as its Cartesian square, and so therefore subsets of the power set, we're going up one type here now, subsets of the power set can be thought of as binary relations on the power set there, simply by thinking of them as sets of pairs of sets from there. And so a partial equivalence relation is a subset that gives you a relation, a binary relation that is symmetric and transitive. In other words, when you take a partial equivalence relation, you don't say that x is equivalent to x overall. You only say x is equivalent to x for certain subsets. And so you can think of the partial equivalence relations as representing quotients of subsets of the power set of n. There are a lot of crazy quotients. Things go far beyond topology and computability there, but they're all there. But what I realized is that the partial equivalence relations, and I wrote this in a paper in the mid-80s there, gives a very quick example of a category, Cartesian closed category, by defining function spaces as partial equivalence relations. If only we had time to do this course, I could show you they're very simple proofs that you stick with equivalence relations, proofs that I like very much. If I teach first order logic, it's pretty boring most of the time, because most of the theorems in logic books on first order logic are just general principles like 2 quantifiers compute or something like that. Who cares? But when you start developing properties like this in terms of the equivalence relations, there's a lot of nice proofs in first order logic to do to show that you have equivalence relations. In particular, equivalence relations can be made into products and sums. Products just means you take 2 copies, 1 copy on each thing, and sum means you take a union of disjoint copies, and it's very easy to write down in this notation with the continuous operators on it so that you show that you have partial equivalence relations, and then the functions between them give you use the continuous functions, I should have said that, the continuous functions on the power set there to say a mapping from A to B is just an enumeration operator that respects equivalence. What else would you say there? And you can get lots of exercises of basic category theory here by doing it in terms of partial equivalence relations, also in terms of infinite products and infinite sums. So you can introduce pi and sigma for families of equivalence relations. So you see we're doing some higher order logic here. We were just on one level with power set of n, but in order to do these equivalence relations, we're going up to sets of sets. But you don't have to go very far up the types to get a rich interpretation of things like Martin-Löf's type theory with dependent sums and dependent products. And now, again, they're very good exercises there. You can cascade these things. A system of dependent types says A is a type as a quotient of a subspace. A is a type and B depends on A. In other words, equivalent elements in A give you the same types B. Now C can depend upon A and B, and then D can depend upon A, B, and C. And so you have a system of dependent types. Martin-Löf and certainly de Bruijn did those kind of things all the times in formulating various axiomatic presentations here. So in terms of this interpretation and the model there, you now have a nice exercise to show that if you take sigma pi, you have a coherent partial equivalence relation. So again, elementary exercises that give you properties of dependent type theory. And in particular, you can think of the dependent types as propositions, namely finding a member of a type could be reinterpreted as asserting a proposition that the type is non-empty. And when you think of it that way, then product and sum are conjunction and disjunction, and function space is implication, and the pi's and sigmas are quantifiers. And so this is the realizability interpretation of intuitionistic logic over the theory of types introduced in this particular model. And you can use the fact that the types form a complete lattice in order to have infinitary polymorphic types. I don't have time to say anything about it, but the complete lattice property of the types gives you a good way to get interesting questions about polymorphic types. And then I don't have too much time at all to give any details here, but I'll try to convince you that it makes perfectly good sense. Everybody knows what numerical valued random variables are that are used in probability theory. But maybe you didn't realize that if you use Boolean-valued logic in terms of the measure algebra of measurable sets modulo measure 0, the measure algebra gives you an interpretation of logic and quantifiers that you can extend to higher order logic using that Boolean algebra. And lo and behold, if you just take what we ordinarily do in two-valued logic for defining the real numbers, the random variables model the real numbers of the Boolean-valued logic over the measure space. So, we know that random variables are well behaved because addition and multiplication are continuous, and so sums and products of random variables are measurable functions, are random variables. But if you interpret things in Boolean-valued logic, then the random variables are just a model for real numbers. It's a complete field with lots of properties that we usually give when we do higher order discussion of the real numbers there. Now, with the lambda calculus, it's exactly the same. Professor Curry would probably turn over in his grave if I stood by his grave and shouted, "Random combinators." But it's perfectly easy. The power set is a topological space. You can define random variables with values in the power set. And because application operation is continuous, as I was explaining to you there, then the full apparatus of lambda calculus can be applied to random variables, taking values in power set of n. So therefore, Turing's idea that he would like to introduce random parameters into computations can be coherently realized by using random variables and the power set model of lambda calculus. So, with a group led by Prakash Panageddon, we're trying to develop applications of that. It's still a little bit early days and much more is going to be done. I'm going to meet with Madare and Furber in Berlin next week there to think about the next things to write. But if you want to look at a little bit of that, this symposium paper has it, and Madare can always be contacted if you want to get further with that. So now I'll conclude finally here. A little bit of topology gives me the lambda calculus. A little bit of logic with types gives me the category of types. I showed you with a little bit of recursion you get to computability, and the point is that the power set of n as a universal space allows the subspaces and the types to inherit automatically a certain amount of topology and a certain amount of computability. There are many horrible subtypes of the power set of n. Pay no attention to them. There are lots of nice subsets of the power set of n where you can discuss topology and computability. On it, polymorphism gives you inductive and co-inductive data structures, and the use of types this way gives you a modeling of constructive logic. So what I'm trying to say here is, with a little bit of power setting, you have a laboratory to understand these things, where you have to give serious proofs to get the properties of these things. But you don't have to have very abstract logical formulations to do it, because I say that the power set things are quite concrete. And if only I still was young enough to have graduate students, and there I would love to do all of the arguments that I've been telling you about here, to implement them in computer-based theorem proving, because the HOL, Isabelle systems, for example, and other systems are perfectly set up to automate proofs of the things that I've just been telling you about. And I wish I could have such a project, but I have to leave it to the future, maybe to someone in the room, I wish. Thank you for your attention today.